Hello students, in this lecture we will see the next point, that is mathematical derivation of current gain factors. So in order to discuss or see the mathematical derivation of current gain factors in a transistor, first one has to take into consideration a transistor, say NPN transistor. So this figure 1 shows various particle flux component in NPN transistor. So the various particle fluxes are JNE minus, then JNC minus, then JG plus, again JR minus, and JRB plus, again JPCO minus. So these are the various particle flux, that is when this NPN transistor is in active mode, say this is a junction J1 and this is a junction J2. So when this NPN transistor is in active mode, junction J1 is forward biased, and junction J2 is reverse biased. So when this NPN transistor is in active mode, that is this junction J1 is in forward bias and junction J2 is in reverse bias, the electrons which are crossing from this N region to P region forms the particle flux which is given by JNE minus. Then as this is a N type semiconductor and the majority carriers are electrons, when these electrons crosses this junction J1, that is junction between this emitter and base, and this is a collector. So when electron crosses this emitter base junction, some of the electrons will recombine with the majority carriers in this base, that is, as the base is of P type, there are holes are the majority carriers in this region, and some of the electrons which are crossing this junction J1 will recombine with the holes in the base, and remaining electrons will try to cross this junction J2. So the electrons which try to cross this junction, that is base collector junction, forms the particle flux which is given by JNC minus. Again, as this junction J1 is in forward bias, so at the emitter base space charge region, there is a possibility of recombination of electrons and holes which forms the particle flux which is given by JR minus. Again, as during the recombination of electrons from emitter and holes from base, in the base there is replenishment of the holes which are given by the base terminal which is given by JRB plus. That is, JRB plus is the particle flux which compensates the holes which are lost in the recombination process when electrons from emitter comes to the base and recombines with the holes. Some of the electrons which are lost in the base and that are replenished by this particle flux which is given by JRB plus. Again, as this junction J2, that is base collector junction, is in reverse bias, there is generation of electrons and holes. So this yields the particle flux which is given by Jg plus, and finally the ideal reverse saturation current in the base collector junction is denoted by JPCO minus. So before going to discuss this, there seems to be a large number of flux component which may help to clarify the situation, and the correlating this flux component with each other with the minority carrier distribution which is given by this figure 2. So this figure 2 shows the minority carrier distribution in an NPN transistor operating in active mode. So in this figure, this is the NPN transistor which is working in the active mode, and there are different regions, that is which are denoted by x is equal to xe dash, that is this is the limit of xe dash, and this x dash is equal to 0 to x dash is equal to xe dash is the region which is the emitter of the transistor, and this curve shows the minority carrier distribution in the emitter, that is this is the distribution of holes, because hole is of n type and there is minority carriers are holes. So this is the distribution of holes in n region or in emitter. Then this curve shows the minority carrier distribution in p region, that is the distribution of electrons in the base which is given by this curve, and this curve shows the minority carrier distribution in collector. This is the collector and this is the base. As the collector is of n type, this is the minority carrier distribution or hole distribution in the collector. So we have already discussed the number of factors, that is particle flux. So the electron flux which are injected from emitter into the base which is given by JNE plus. As the electron diffuse across the base, few of the electron will recombine with the majority carriers in the base, and the majority carrier holes that are lost by recombination must be compensated or replenished from the base terminal, and which is given by this JRB plus. This particle flux JRB plus is nothing but the number of holes which can be replenished by the base terminals. So this replacement of hole flux which is denoted by JRB plus. The electron flux that reaches to the collector which is given by JNC minus. The majority carrier holes from the base that are injected back into the emitter results in the hole flux, and which is denoted by JP plus. So JP plus is the majority carrier holes from the base that are injected back into the emitter, which results the particle flux, that is JPE plus. Some of the electrons and holes that are injected into the forward biased base emitter space charge region will recombine at this emitter base space charge region. The generation of electrons and holes occurs at the reverse bias base collector junction. That is, this junction is the reverse bias junction, and there is generation of electrons and holes at this junction. So this generation yields the hole flux, which is given by Jg plus. So due to generation of electrons and holes at this junction, we found the particle flux, that is Jg plus. Again, the ideal reverse saturation current in the base collector junction, which is denoted by JPCO minus. So the corresponding electric current density component in the NPN transistor is given by this figure number 3, which is identical to this figure number 2. So in this figure we found the curves are same as in figure number 2, and as in the PN junction, the current in the bipolar transistor are defined in terms of minority carrier diffusion currents. So the various current densities which one may can define, that is JNE, which is due to the diffusion of minority carrier electrons. JNE is the current density which is due to diffusion of minority carrier electrons, minority carrier electrons in the base at x equal to 0. Then next is JNC. So this is JNE in figure number 3, which is due to diffusion of minority carrier electrons into the base at x is equal to 0. Then next is JNC. So this current density is due to diffusion of minority carrier electrons, diffusion of minority carrier electrons in the base, at x is equal to xb, x equal to xb. Then JRB, the current density which is due to flow of holes, into the base to replace the holes into the base replace the holes, to replace the holes lost by recombination, lost by recombination. Again, JP, which is due to diffusion of minority carriers, JP, which is due to diffusion of minority carriers in the emitter minority carrier holes in the emitter at x dash is equal to 0, at x dash is equal to 0. Then JR is current density due to recombination of carriers, due to recombination of carriers in the forward biased base emitter junction. Again, the next current component is JPCO. So JPCO is the current density due to diffusion of minority carrier holes, diffusion of minority carrier holes in the collector at x double dash is equal to 0. Again, JG is the current density due to generation of carriers, in the reverse biased base collector junction. So these are the various current components in NPN transistor. The currents JRB, JPE and JR are the base emitter junction currents only and do not contribute to the collector current. And the currents JPCO and JG are base collector junction currents only. So these current components do not contribute to the transistor action or the current gain. So I will stop here, and in the next lecture we will see the detailed mathematical derivation of current gain factors. Thank you.